Hello once again, our most developed student. My name is Confident. Welcome to the last session of the revision session of this engineering science paper, which I'm looking at question number 7 to question number 9. It means if this is your first time to come in contact with this video, it means you have missed out about 6 questions, but these are made up of 2 videos. I did 2 videos from question 1 to 3 as well as question 4 to 6. So I'll encourage you to go through those videos, and the easiest way is for you to subscribe to our channel, 24-minute lesson, so that you can be notified by YouTube, especially when you turn on that notification bell. You will be notified every time we post a new video. So you guys, if you are benefiting and if you have been watching this channel and gaining some kind of ideas, some strategies, and these have been working for you, please don't forget to subscribe, because it helps us to know that there are people behind this channel who are actually benefiting. If you don't subscribe, it becomes difficult on how to evaluate our work. So please, by subscribing, you are doing a lot. In a way, it's a motivation. We just reached 10,000 subscribers. Can you think about that? It means 10,000 people are benefiting from the channel. But if you look behind the scenes, you can see that it's quite a lot. It's actually 3 times that number, because some they choose not to subscribe. Still fine, but we're saying when we see these subscribers, it kind of gives us a motivation to bring more content for you in a way that can make you benefit. And also, don't forget, if you want some of the videos, they're available for Prime members. If you are a Prime member, it means you make monthly contributions to the channel. It's as low as 29 or 39 rand, which is very minimal as an entry. What it does is it helps support this channel. So some of you who wants to join, I have given the steps. You can check on the steps that I'm showing here to say how can you become a Prime member. You click on join, and then you can now choose the pack or the package, whether you want N1. If you do N2, it means you will automatically benefit for N1 and N2. If you do N3, you benefit from N1, N2, and N3, just like that. Alright, enough about that. Some of you are complaining already, saying please just take us through the video and stop saying all this unnecessary thing. Alright, there we go. I'm going to do just like that. Let's look at a few questions now. The content or the topic here is on heat, and we are looking at question 7.1. It says explain the term heat lost. It's one unique, in a way, more like there is no definition as such, but it's more like you are explaining. It's not really a definition, but they want you to explain the way you understand heat lost. It's an open question, I'll say. But when we're talking about heat lost, we are saying it is when a substance, remember heat is identified with temperature drop. So it is when a substance loses or decreases, loses heat. I'll say first loses heat. It's when a substance loses heat or drops in temperature. When a substance loses heat, or when it drops in temperature from the initial temperature. So when we are looking at heat lost temperature, so when we are looking at heat lost, we are saying there was a higher temperature here and the temperature has dropped. So that heat that has been lost is called heat lost. So it's an open question. One can say heat lost is when an object, we can say here, when an object's temperature drops. It's when an object's temperature, when an object's temperature drops from high to low, just something to low, just something that just identifies that there was a higher temperature before, now it is a lower temperature. So that's what, in a way, you are trying to do. Now, let us look at question 7.2. Says define the term specific heat capacity. See, now this is a definition. They are not saying here explain, they're saying define. So you need to give us the exact definition. We are saying specific heat capacity is the amount of heat required to raise the temperature of a substance. Actually, it's the amount of heat required to raise the temperature of a 1 kilogram substance. It's very important there, that 1 kilogram substance is the amount of heat required to raise the temperature of a 1 kilogram substance by 1 degree Celsius. So specific heat capacity is the amount of heat energy required to raise a 1 kilogram substance by 1 degree Celsius. Very important definition. You definitely need to know that. That is the specific heat capacity. And then we move on to question 7.3. Here it says, I think these are calculations now. It says a 40 kilogram welded steel. So let's look at that as the keyword. It's a 40 kg welded steel. Okay, steel plate. You need to know what you're dealing with. So it's a 40 kilogram welded steel plate with the temperature of 94 degrees, is dipped in water. So there is water, is dipped in the water container with the water temperature. There is the water temperature being 18 degrees. The final temperature of the water, so the final temperature of the water and steel is 60 degrees Celsius. Now, before you do any calculations, usually what I prefer, especially in this section, I don't do it much, but I do it mainly in this section, whereby the formula already you can see here, there are two different things you are dealing with. You are dealing with steel and you are dealing with water. So now what you'll be wanting to do is to separate whatever. So what we have, they're saying here, the mass of steel, I'll say MS, is 40 kg. I think that. And then with the temperature, so the temperature, the T of steel, I'll call it T1 of steel. The temperature there is 94 degrees Celsius, is dipped in water. Now let's go to the water with the temperature of, now underwater, T1 of water of W is 18 degrees Celsius. You see what I'm doing? I'm trying to separate this data. And the final temperature of water and steel, so which is T2 of water is 60 degrees Celsius, and I'll say T2 of steel is also 60 degrees Celsius. You see what I'm doing there? Now with this, it becomes then easier for you to do your calculations if you captured everything. So now it says calculate the mass of water in the container. That's 7.3.1. They want the mass of water in the container. Now the moment you're going to deal with such, there is a formula that you must know whenever you're dealing with this. Now look at this. They are saying you have a cup here or whatever, and you are introducing, there is water already here. So now they are saying this water is at what? It's initially at 18 degrees. So now you're going to bring a very hot object inside this water. Let me make it red. It's a hot object. So the moment you take it inside the water now, you know, it's very hot. So it raises the temperature from 18 degrees. The temperature goes up to 60 degrees. You're seeing that? And then obviously the object here was at 94 degrees Celsius. It means the temperature of the object also actually dropped, but that of water increased. So when you are looking about changes in temperature, there is the general formula. I'll write it at the center here, which says what? Let's look at the formulas. This is a common formula. There it is. Let us put it. Look at this formula here. That's the formula that you need to rely on here. So it says what? Q is equal to MC change in T. So I'm going to write that formula here to say Q in the center is equal to MC change in T. But now you can see that steel loses, so it's heat lost. Remember they were saying define that. And water is heat gained. Do you see that? So I think the assumption on these questions is that no heat is lost to the surrounding. So you can come with a formula which says heat lost is equal to heat gained. So whenever we're dealing with such questions, when one object loses, the other one gains. So now this formula then is going to remember Q represents the heat. So in this formula, the Q part, you can say Q lost, which is heat lost, is equal to Q gained, which means heat gained. But where there is Q, you know that Q is MC change in T. So if I say MC change in T, this side is for lost, is equal to MC change in T, and this side is gained. Now what is the question requiring now? Because it's always that, but what do you need? They say calculate the mass of water. They want the amount or the mass of water in the container. So they're asking how much of this water is in this container to cause such changes. So what you do here, you can see that you are looking in this stage on this side of water, you are looking for M. So now let's substitute the data that were given. We have on the left hand side the mass of steel, which you are going to then say it's 40 times C is the specific heat capacity of steel, and on the other side C is the specific heat capacity of water. So we need to identify the specific heat capacities. It's in the first page where there is some data there. If you look at that, you'll get two important information there. It is the specific heat capacity of water and the specific heat capacity of steel. You can see that of steel it's 500 joules per kilogram degrees. So 500. So I'm gonna have here and say times 500, and then times change in temperature, means final temperature minus initial temperature, meaning T2 in here. Now you can do that T2 here, change in temperature is T2 minus T1. You can write that formula like that. And then here also T2 minus T1. So change in temperature, or you can actually write and say T2 minus T1 is equal to what? 94 minus 60. And then it can give you actually the change in temperature straight away to say 94 minus 60 equal to 34. So you can have 34 degrees this side. You come here again, T2 minus T1, which is equal to 60 minus 18. And if you do that, you can also get the answer to say 60 minus 18 is 42. It's up to you how you want to do it. So I can actually now use 34 there, change in temperature there, which is our change in T. So this is our change in T is equal to T2 minus T1. That's the change in T. So we have got 34 there. I can then remove this bracket. So you had two ways of writing it. You could have written it like this to say times, and then you come here and say 94 minus 60. I think that it was allowed like that, but since I've already subtracted, I can write the answer to that, which is times 34 is equal to the M that we don't know, which we are calculating the M of water, times C of water. We come back again to the specific heat capacity. You see of water it's 4187 joules per kilogram degrees. So 4187, 4187, it's a Comilla figure, times change in temperature, like we did, we say this is 42. So how do you find the mass of water? Now look, everything is multiplying on the left and on the right. Now the opposite of multiplication, as I always say, is division. Now to get rid of 4187, you divide by 4187. Also to get rid of 42, you divide by 42. So you see, that will go, that will go. What you do on the left, you do on the right, over 4187 times 42. So when you do that, it then in a way gives you now a part to say, if you have to look into that, I'll just have to use 1. So it's 40 times 500. Actually, I must use, yes, that this is 40 times 500 times 34. I think that over 4187 times 42. Are you getting that? Which is equal to, there it is, 3,8668. So it's 3,8 shift setup. Remember, rounding off is number 6. And 3 decimal place is 3,867. So that's what I want to write there, 3,867. So the answer there is 3,867. And what is that? It is equal to m of water. But now remember, mass is always measured in what? In kilograms. So which means, therefore, the question was what? Calculate the mass of water in the container. You can say, therefore, mass of water is equal to 3,867 kilograms. This was the mass of water in the container. Done. How many marks? You get 3 marks for that. Not bad, but yeah. Now, okay, let me undo this. Maybe it will still work. Now, the next question they ask here is, calculate the energy gained by the water. See now, it's a continuation. Calculate the energy gained by water. And we used this formula here about energy. Remember, we said the energy gained, which is heat gained. You can see that heat gained, it's Q here. Let me use a different pen here to say heat gained. It's Q is equal to MC change in T. Now we know the M, and what was the M? Is 3,867. So you say 3,867 times the specific heat capacity, don't forget, is 4187, times change in temperature, it was 42. We're still using the same values. Now if you say what's the answer there, it will give you 3,867 times 4187 times 42. This will give me 680,027. So it's 680,027,418. So it's 680,027,418. I hope I'm doing that. Remember, we're talking about Q, which is the heat energy gained. So you can use the answer as Q there is equal to blah 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 joules. You can convert it to kilojoules, which you divide by 1,000. I think it will give you 680,00, because the 0 will be there. If you divide by 1,000, 003 kilojoules. It's up to you how you want to bring the answer into that, whether to joules or you want to leave the answer in kilojoules. That is that. Or you can actually have used the other one here. Remember, heat lost is same as heat gained. So I could have used actually this one to say the amount of heat that is lost is the same amount of heat that is gained. So I could have used that to say Q is equal to the M that is lost rate was 40 times 500 times 34. If I just use directly the same numbers that I used on this other side, I'll have 40 times 500 times 34, which is 680,000. This is straight. It's 680,000, which is equal to 680,000 kilojoules. So you say the answer is almost the same because there is no heat lost in this case. So it depends how you want to approach it, but yeah, that is that. So having done that, if I can erase here, let's move on to question 7.4. It's a new question here. It says a copper rod with a length of 5 meters and a temperature of 20 degrees is exposed to heat with a temperature of 400 degrees. Calculate the change in length of the rod in millimeters. Again, here you need to put some information together. So what you have a copper rod, you underline that. Then the initial length, this is called L0, that's the initial length, and the temperature T there, that is your T0 or T1, let's call it T1, is exposed to a heat with a temperature, let's call it T2. So let's do that. L0, you have got 5 meters, and you are dealing with a substance called copper, where the L0 is 5 meters, T1 is 20 degrees Celsius, T2 is equal to 400 degrees Celsius. So now you can do that thing of saying change in temperature is T2 minus T1. Do you see that? Which is what? 400 minus 20, and then 400 minus 20, I think there is 380 degrees Celsius. I think that. So far so good. Now you wanna use the formula. The question is, which formula are you going to use? Come back again. You're still not far from where you were when you're doing that, but this is the formula now to say, let's look at the question actually. The question says calculate the change in length. The word change is delta L, change in length of the rod in millimeters. So change in length. So we come here, there are two formulas that we can use which have got change in length. You see there is L, change in length is L0 times that, or LF is that. But because we are just interested in the formulas we have to use the first one. Change in length is L0 times alpha times change in T. And when you're talking about that, I'll come back to that to say change in length. Let me write that formula first. Change in length is equal to L0 times alpha times change in T. Just to cross check that. And then when we are looking at alpha here, you come back to your formulas, and then we're looking at the coefficient of expansion, and we're talking about which substance was this? It was copper. So you look at the linear expansion and you focus here on copper, and that is the value, right? 0,000017 per degree. So it's 4 zeros and 1 7. So here how you write it, you say change in L is L0, which is 5 times that linear coefficient of expansion of copper. That's the one, the alpha that we say it's 0,123017. Let me see that. It's after the decimal, it's 4 zeros and 1 7. So it's 4 zeros and 1 7. You see? And then times change in temperature, we did say is now 308, which is that. Change in length. Then you can now finalize that with the calculator to say 5 times 0,123,417 times 380. And then from there you get 0,0323. 0,0323. Now this is change in length, not change in temperature. So we are looking here at change in length. So change in length is equal to that. Now remember, by default, or the SI unit there is going to be meters, but they said use what? You need to give your answer in what? In millimeters. See that? So you're going to say 0,0323 multiplied by 1000, because these are meters, to change to millimeters, which is 32.3. So which is equal to 32,3 millimeters. That is the change in length there. I hope, guys, this is making sense to you. And as we're moving on to the next lesson, just remember to subscribe again so that you can benefit more of these, and also ensure that you turn on that notification bell. All right, now we are looking at question number 8. We are continuing, but question 8 is one of the simplified topics, the particle structure of matter. They don't go deep in it. It's just a part of chemistry that they just kind of introduces it and leave it there. It's similar with N1 as well as N2, but look at this. It says define the term atom. So what is an atom? An atom here, you are saying an atom is the smallest, very important that word, is the smallest particle of an element. You need just to find the definition that you'll use, but simple like that, the smallest particle of an element or of a compound, or but an atom is the smallest particle of an element. Yes, can be an element, a compound, or whatever, but the key word there is the smallest particle of an element. Okay, then question, that was 1 mark, not much. Atomic number. Now remember, you've got atomic mass and atomic number. Now the atomic number, this is the number of protons in an atom. Number of protons in an atom. Okay, so the atomic number is the number of protons in an atom. Also, how many marks? It's 1 mark. Basic. Yeah. Now we are looking at 8.3. 8.3 says give the constituencies of an atom and their charges. Very common question. Now when they're saying constituencies, they are asking you what is an atom made up of. Now there are 3 things that an atom is made up of. It is made up of protons. These are the constituencies. It is made up of what? Of neutrons. And it is made up of what? Of electrons. All right, and then now they are saying, and their charges, and then you are going to say protons are positively charged. Just avoid this thing of trying to do it so fast, you know. Positively charged. In as much as you know it, just put your answer in full. This is 6 marks and you don't want to lose anything. Neutrons, what are you gonna say? I think you already know the answer. Neutrons are what? Are neutral or have no charge. And then what are you gonna have as the last one? Electrons. What are you gonna say? Electrons are negatively charged. Negatively charged. You know, those are the things that you want to show here. That was the question 8.3. And just going out of this topic in here, sometimes they ask this question in a different way. They'll say draw an atom and indicate its constituencies. So what you do is they'll be expecting you to draw an atom, to say you have here a circle, And then in the circle, in the center here, they expect you to say protons and neutrons. Remember, you write them protons, you write neutrons, and then you indicate with an arrow to say this is the what? But this is not necessary. Remember, I'm just going ahead here. This was the nucleus. It has protons and neutrons. You can put a positive there, and then you indicate now like that. Actually, one is enough. Let's not put many. You just do this, and then you say this is electrons, and okay, and then this is a shell or orbit, but not much, not a mass. But that's the main thing what they are looking for whenever they say label the nucleus, to say it's got that and that, and the electrons. Sometimes they'll say with the signs. That's when you introduce to say these are negative, positive, and neutral, but anything that can give you the answer. Now guys, again, don't forget to get such. Please become our member by subscribing. Question 9. By the way guys, this is the last question. As you can see, this is out of 100. So if you have to do question 9 and get everything correct, it means you are good for a distinction. 9.1, it says give 4 factors that affect the resistance of a conductor and its relationship with the resistance of a conductor. So first of all, this question is in 2 parts. Look at the marker location, it's 8 marks. It says give 4 factors that affect the resistance of a conductor. We are going to end there. What are those factors? And then the next part says the relationship of those factors with the resistance of a conductor, or how do the 4 factors affect the resistance. So in the first part, you're just stating them. Then after that, you tell us how do they affect. But now you don't need to cram as such. Let me show you what I usually use whenever I talk about the resistance of a conductor. I think it's somewhere here. There we go. I use this formula. It helps me to know the resistance of a conductor. Say R is equal to P times L over alpha. Let me write it down here. R is P times L over A, not alpha. Look at this. From here, I can tell you the factors that are affecting the resistance. R is the resistance of a conductor. Let's do with the first easier one. L stands for length. We're going to call it 1. Number 2, we're going to discuss the second part. What is number 2? Number 2A stands for area. Are you with me? Number 3, what does number 3 stands for? P is the type of material or the which is affecting the resistivity. That is resistivity. And then what is number 4? Temperature always plays a role, though it's not included here, but it is assumed that whenever you are doing these calculations, the temperature remains constant. So now here, the question is done saying list 4 factors that affect the resistance of a conductor. So these are the 4 factors, and then how is their relationship with the resistance of a conductor? The relationship is on this formula. Look at it. If it's on top, if R is equal to P, you are saying, and L is equal to L, and R, the ones on top here, we say they are directly proportional. I seen that. That's the relationship. And the one at the bottom is inversely proportional. So let's start with the length to say here, how does the length affect? We are saying the length of a conductor, just to put it right, is saying the length of a conductor is directly, remember we said when they're on top, they're directly, is directly proportional. The length of a conductor is directly proportional to resistance. That's the first part. That's the relationship. You mentioned the same thing. What about resistivity? is still the same thing, is on top, saying resistivity is directly proportional. By being directly proportional, you see, when resistivity increases, it means also what? The resistance will increase. Resistivity is directly proportional to resistance of a conductor there. And then I'm just going to go ahead here. I'll come back to area. Look at temperature. It's also the same. Temperature is what? Is directly, just know, temperature is not indicated there, but temperature is directly proportional. Just remember that. Temperature is directly proportional to resistance, and then area is the one that is changing. We are going to say area, as you can see here, is inversely, I think that, proportional. Area is inversely proportional to resistance. This is the relationship that they're trying to do. Just, it's easier, something you're already knowing, but you needed to put it in a formal way the calculator wants. The answers want. Now 9.2, it says indicate whether the following statements are true or false by writing only true or falseness to the question number 9.2.1 to 9.2.2 in the answer book. Now let's look at 9.2.1. says two resistors of 8 ohm. Want to check two resistors, it's 8 ohm and 4 ohm, are connected in parallel, and total current of the circuit passing through is 3 amps. The voltage is 8 volts. Let me repeat. They're saying indicate whether is it true that two resistors of 8 ohms and 4 ohms that are connected in parallel and total current passing through is 3 amps, the voltage will be 8 volts. We can test that. So picture like this. They're saying two resistors connected in parallel, so I can have that, and then I can have that. So these resistors are connected in parallel and the total current passing through. So if you do that, you can actually do like this. And then here is the voltage. So they are saying it's, let's say, plus or minus. So there is the current I. So they are saying the current is 3 amps. And then this is 8 and this is 4. So they are saying this is 3 amps. They are saying that particular voltage here will be what? Will be 8 volts. So let's prove that L 8 volts. Now obviously we have to use our formula here, which says resistance is voltage over current. First things first, let me see here. If it's not there, I'm not seeing it, but it's fine. The first one that we're going to use is parallel resistors, which is this one. 1 of Rp is 1 over R1 plus 1 of R2 plus 1 of Rn. These are parallel resistors, okay? So I'm going to use here to say total resistance here, it's 1 over R parallel is equal to 1 over R1 plus 1 over R2. So 1 over R, the parallel, is equal to 1 over 8 plus 1 over 4. I think that. And then with that, I've got 1 over R parallel is equal to, and then I can then add these two to say I've got 1 over 8 plus 1 over 4. So I've got 3 over 8. So this is 3 over 8. So which means, how do I find R parallel? It's easy. The simplest way I always tell students to do is take the R parallel to the top and take the 1 to the bottom. Nothing will change. So you'll have R parallel over 1, which is as good as R parallel. But you know what you do on the right, you do on the left. So you take the 8 to the top, take the 3 to the bottom. So this is R parallel is equal to 8/3. We can leave it like that. I think that. So which means here I can redraw this diagram, and this diagram will be now looking like this, to say here I've got total resistance, which is 8/3. Okay, let me write it on inside here to say this resistor is 8/3, and then if the current here, if this current is a plus or minus, if this current is 3 amps, what will be the voltage there? Now remember, you use that triangle here, which says what? V here is equal to IR. Remember that formula to say if I want to find my voltage, it is equal to I times R. So now my voltage I is 3 times the R is 8/3. Seeing that, which is equal to, this is 3/1. If you multiply, you get 8. V there is equal to 8 volts. So the statement is correct because actually our V is also 8 volts. So this statement is true. Here, it's true. So you're going to say 9.2.1 is what? It is true. Let's go to 9.2.2. Let me just erase here. 9.2.2, it says, in a simple DC circuit, it is found that two resistors with each having the resistance of 10 ohms are connected in parallel to each other. So there are two of them each having that. So they are connected in parallel to each other, and the parallel combination is connected in series with another resistor with a resistance of 5 ohms. The total effective resistance of the circuit is 10 ohms. They are saying, is this true or false? So what they are trying to say here is, you have a circuit, two resistors with each having 10 ohms. So let's look at these resistors. There is my resistor here. It's 10 ohms. They are saying they are connected in what? In parallel to each other. There is another one with 10 ohms. So two resistors are connected in parallel to each other, and this parallel combination, this parallel combination is connected in series. So you have now a series flowing out with another resistor, which is what? Let me make it smaller, not too big. This is 5 ohms. Now, what is the total effective resistance of this? So what you're doing here is, you are looking at this and say, okay, if I can then have a complete circuit like this, what will be the total effective resistance? This is plus and minus. So you know, when current start flowing, the moment current comes here, it will split. That's why we're saying these resistors are in parallel. So you need to use that formula for parallel for this one. The formula is 1/R parallel. Remember, it's 1/R1 plus 1/R2. We just did it. 1/R parallel is 1/10 plus 1/10. And then what is 1/R parallel? Is equal to, then you get that 1/10 plus 1/10, just to get the answer there. So it's 1/10 plus 1/10. It gives me 1/5. So I've got here 1/5, and I told you what to do when it's like that. Take R parallel to the top, take 1 to the bottom, meaning you will have here, let me give it a bit like that, meaning what you're going to have therefore here is to say R parallel is equal to 5. Okay, when you do that, take 5 to the top and take 1 to the bottom. So R parallel is equal to 5. 5/1 is same as 5. So R parallel here is equal to 5 ohms. So what you have, you will have now a combined system. This gives a 5 ohms. So you can erase this and say this parallel combination, if I can have a resistor, that particular resistor will be what? It will be 5 ohms. You see what's happening? Now this one, now they are in series. You know the total resistance for series. We have the formula here to say resistors in series. That's why it's RS. It's R1 plus R2 plus R3 plus up to Rn. So here we also use the same to say RS. Use another one to say the resistor in series is equal to R1 plus R2, which is equal to 5 plus 5, and the resistor in series therefore will give me 10 ohms. This 10 ohms is our effective resistance. Okay, so if they are asking you the effective resistance or the total resistance, we are saying is 10 ohms. Now let's read the statement. In a simple DC, it is found that the two resistors, each having the resistance of 10 ohms, are connected in parallel to each other, and the parallel combination is connected in series with another resistor with resistance of 5 ohms. The total effective resistance of the circuit is 10 ohms. This is true. So you come here and say 9.2.2. It is what? It is true. So that is how you got your 4 marks. I like that kind of question. Yes, you can guess your way in or out, but it's good to always draw them so that they look more real and everything. Last question, 9.3, 1 mark. It says name one example where mutual induction is used in practice. So here they are talking about an example of what? They are talking about an example of mutual induction here. And whenever we're talking about mutual induction, this is generation of electricity, and we are actually looking at one thing that can use that is a transformer as the best for mutual induction. Transformer is the answer here, because with the example, whenever you are learning about mutual induction, they will actually link you back to say a transformer is the best example of mutual induction. This brings us to an end with a total of 100 marks. And guys, you be the judge. How was this paper? Given an exam, will you be able to ace it? Will you be able to get a distinction? I always feel like you guys can do so. You can be in a way struggling, you know, as an underdog, but distinctions are also possible if you prepare well. Remember, 5 P's. Proper preparation prevents poor performance. So prepare in time so that you can prevent failure. So some they say proper planning prevents poor performance. So, and again, the failure to plan is the planning to fail. So be careful with your preparations, because what you don't do is as good as planning not to do. I hope you guys are benefiting from this channel. It is always my desire, it is always my kind of adrenaline or my kind of motivation to see you guys getting good marks. So after getting that good mark, please share with us on our channel. Come back and say, how did you fail in that particular exam? Was this of benefit? If so, let us celebrate together. We have come to the end of our lesson. Good luck.